Hello, my name is Charles Maurer. I'm going to help you take a nap today by talking about this book that my wife and I published with Cambridge Scholars. Our goal in Pretty Ugly was to explain why Homo sapiens, and some other animals, develop a sense of beauty. Why and how? Many people have tried to answer these questions, but all of them started with a philosophical theory of some sort. Such theories might be consistent internally, but they're always divorced from basic sciences, from physics and biology. We think that if you can't base an explanation on the physical world, it doesn't explain very much. Instead, we intended to ignore philosophy and provide an explanation of aesthetics based solely on science. It took us 32 years, but eventually we put together a framework of converging evidence. Evidence from a number of sciences and from the histories across culture of all of the arts. In this hour, I'm going to show you some of this framework. As our book does, I shall assemble evidence converging from many directions. If a man from Mars examined you, he wouldn't see a body with a mind. He'd see a chemical machine. A chemical machine with a cauliflower in control. This cauliflower is the core of the arts. He would see that neurochemical signals feed into the cauliflower from different places, the eyes, the ears, but he would see nothing in the cauliflower to keep the signals apart. He would expect that the signals from the eyes and the ears and other sensory organs get mixed up. And they do. For example, vision gets mixed up with balance. You've probably felt this in an IMAX theater. During the aerial shots, you feel off balance, although you're sitting securely in your seat. You can feel the mix-up right now if you try to balance on one foot and close your eyes. Just be sure you have something to grab a hold of nearby. Hearing affects balance too. Octogenarians hear poorly and balance poorly. If you give a university student earplugs that make him hear like an octogenarian, then the student will balance like an octogenarian. The sound of music we often feel in our muscles, which move to the beat. Moreover, we can see in a lab that moving to a beat helps you to hear a rhythm. Sounds are intertwined with vision as well. 10% of people even see colors when they hear music, like this. And we taste sounds. Pringles are synthetic potato chips that are as like one another as poker chips. Yet you can make one taste better than another by making it sound crispier through headphones. We all know that most of what we perceive to be taste actually comes not from the taste buds, but from the nose. Chemical vapors from food travel from the mouth into the nose by the nose's back door above the throat. Vision also affects odors. Pour equal amounts of peppermint concentrate into 2 glasses of water. You can't see it's there. To 1 glass, add some food coloring. The colored peppermint will smell stronger than the clear peppermint, even if the color has no association with mint at all, a color like yellow. That's why industrial food companies use so much artificial coloring. This is Baskin-Robbins' chocolate mint ice cream. I'm sure they didn't choose that color by accident. Their market researchers must have found that to most people, this bizarre hue enhances the flavor. Of course, ice cream is plebeian. You might expect the unwashed masses to prefer an unnatural color. But this is a regal bottle of scotch, a scotch aged 25 years. It costs $3,300 US. Here is the list of ingredients. E150A is caramel coloring. Finally, we can feel through our eyes. In this lab setup, the white hand is rubber. The guy in the red shirt is hiding one hand beneath the table, yet he feels both hands being stroked. He feels the brush on the rubber hand as though it were on his own. All of these senses are mixed up because there is nothing in the brain to keep them apart. Outside the brain, different forms of energy stimulate different forms of sensory receptor, but every receptor sends the same kind of neurochemical impulses into the brain. Within the brain, local specialization is not wired in, it's just an accident of the body's structure. For example, where the optic nerve enters the brain, that region of the brain will be the most heavily influenced by visual information. But if a young child goes blind, that region will become involved with other functions, including hearing. This is the machinery that forms all of our sensations and all of our perceptions, so it must also form all of our aesthetic perceptions. We're going to look at this machinery next. At this point, you may be falling asleep and wanting a good cup of coffee. But what is a good cup of coffee? Each of us knows what makes one, but our ideas vary widely. Here is the range of concentrations that people in different parts of the world think makes a good cup of coffee. On the right is an Italian ristretto. Half that many beans would be a short espresso. The left is the normal gas station brew in Nebraska. The difference in concentration is 20-fold. Clearly, the good in good coffee is arbitrary. This fellow sure wasn't born to like coffee. Bitter chemicals taste foul from birth. He's actually tasting quinine, but it might as well be caffeine. So do acidic chemicals, like this vinegar. All of them taste sour. We are born liking sugars and also savory flavors like meat. Yet most of us learn to like coffee. We adapt to its bitterness and learn to enjoy it. Babies can begin this process while they're still in the womb. Babies are born disliking the smell of anise. They turn away from it and frown. You can see that here. The black bar shows that a group of babies frowned on average 3 seconds when given some anise to smell. In contrast, the white bar shows that they frowned only half a second when smelling nothing at all. But if the mother had eaten anise cookies toward the end of pregnancy, then the baby will not turn away and frown. This shows that learning to like flavors begins before birth. We're not plants that grow tropically toward light. We adapt to our surroundings actively and even proactively. Adapting to our surroundings requires recognizing what we have encountered before, and doing this at every neurological level. Adaptation is a chemical process built into individual neurons of the brain and their interconnections. This is the neuron. Neurochemical energy stimulates some strand of the tangle on the left, then a chain of chemical reactions travels rightward along the long threads. At the right-hand edge, you can see that those threads have split ends. From those split ends, bolts of neurochemical energy cross a chemical soup to stimulate nearby neurons in the same way. This creates a chain reaction that spreads throughout the brain. When a bolt of neurochemical energy blasts from one neuron to another, it changes the chemicals in its path, and it changes the chemicals alongside its path. If this happens often enough, the chemical structure cooks solid. That is the mechanism of adaptation. But it's not enough to adapt to normality. To survive, the brain must become especially sensitive to slight differences from normality. Not big differences, but slight ones. Imagine you are one of our ancestors in Africa. You head toward a stream where there's this bump in the water that suddenly appears. You need to notice it instantly, and you need to interpret it instantly. Is it useful or dangerous? You notice it fast because it disturbs the average appearance of the water by sticking up. You can't be certain immediately whether it's a floating log or a crocodile, but you have learned from experience that crocodiles are mighty fast and mighty dangerous. So without waiting to be certain, you run away. This shows a bias against crocodiles, a sensible bias developed from experience, from seeing a crocodile catch an antelope, a bias that helps you live. This mechanism is required for any adaptive species to survive. Comfort with what's normal, and close attention to anything slightly abnormal. Attention that's interpreted according to learned biases. This is also the mechanism of aesthetics. Experiences accumulate to form an average that feels boringly comfortable. You can see an example here. The woman in the center looks comely, probably comelier than the others. Her picture also has pride of place. Despite this, the other pictures draw your eye. What's happening is this. The woman in the center is the geometrical average of the other four. She is closer than the others to what your brain reacts to as an average female face. Since the other four are more different from that average, you look at them harder. How you respond to those other faces will depend upon how your personal experiences have biased you. One of them may resemble a teacher you detested. She you're likely to find particularly homely. On the other hand, another may look like your mother and her sisters. You're likely to find her more attractive than the others. That is the mechanism of aesthetic perception. That is the mechanism of all aesthetic perception. For example, we can see it here with 20 seconds of synthesized Chopin. You'll get used to this rhythm rapidly, so it will function in this context as a norm or average. However, a slight modification makes it more interesting. A slight modification that our experience has biased us to hear as more beautiful. In contrast, a comparable modification in the opposite direction is also more interesting than the average, but it is hardly beautiful. In short, beauty is average with a positive twist. Ugliness is average with a negative twist. We can see how experience forms bias, and how easily, from a study Daphne did with undergrads. Ostensibly, this was a study of memory. She asked undergrads to look at and remember 40 faces. Each of those faces might have had its features in a normal position, like the one in the middle here, or each of the faces might have been modified like those on the ends. You see faces with features so high or so low in only 5% of the population. Again, any one student saw only one of the heights. Daphne asked the student to keep track of how many times he saw each face, after which she asked a few questions. But that was just a ruse. The real experiment came next. She said, "You didn't really spend the normal amount of time to get a course credit for participating in an experiment. Would you mind participating in another quick one?" In the second experiment, the real one, Daphne showed one of these faces on a computer. On the computer, the features were not fixed. Sliding a mouse would slide them up or down. Daphne asked each student to put the features in the most attractive place. Students who had seen faces with high features put the features higher, and vice versa. Those who had seen the normal faces put them in the middle. Just looking at those 40 pictures was enough to change someone's biases and notion of beauty, at least temporarily. Here we can see how this plays out in the real world. Here are ideals of body shape 2 centuries apart. Both show Venus life-sized. Both of these paintings were erotica dressed as culture. Rubens was the height of artistic fashion in his day, and he painted countless nude women shaped like the one on the left. But times change, and fashion changes. The nudes on the right by Bouguereau made such an impression on the men who ran France that immediately after he exhibited it at the Académie, the government purchased it for the nation. Here they are larger. Rubens painted for aristocrats living mostly in rural chateaux. They and some churchmen were the only people in society who could afford to stuff themselves with food, and they did. A fat body connoted wealth. A thin body connoted poverty and hunger, not sex. When Bouguereau painted, French fashion came from Paris, and Paris had become bourgeois. Rich women still stuffed themselves, but the streets were filled with prostitutes, and those prostitutes who served middle-class men could eat adequately, although not abundantly, while they were young. This allowed their bodies to grow normally without getting fat. In this class were many, if not most, artist models and women of the stage. With this societal evolution, the figures of Bouguereau's became the sexual ideal. As we can learn to enjoy what we're used to seeing, so we can learn to enjoy what we're used to tasting, even if it's something so naturally unpleasant as coffee. We become used to a certain concentration of coffee, so this concentration defines a good cup of coffee. But a slight variation might make it great, like adding whipped cream instead of milk. A few times I've mentioned this mechanism to enophiles. All of them have had the same reaction. Nonsense! They're certain that some wines are intrinsically better than others. Just read reviews, they tell me. Of course I've read reviews, but I confess that I can seldom understand them. For example, here is a description of a wine I chose more or less at random from a catalogue. A description by James Suckling, one of the world's most influential wine critics. Quote, "A pretty red that shows raspberries, black plums, chocolate, and iodine." I have no idea what I'm supposed to make of that. What does iodine taste like? Nor am I alone in my confusion. Some researchers in Australia gave the same wine to 29 enologists and asked for the two words that describe the wine most clearly. This is what they found. All of the words in black they used only once. A few of them agreed on a few of the words, those in red. The most common descriptor was plum, but only 1/4 of the enologists used it. Clearly, the descriptive vocabulary of wine critics is personal and idiosyncratic. The descriptors are personal because they're not describing natural categories. There is no natural taxonomy of aromas. This is the closest I could find a standardized system devised by U.S. academics. To see how arbitrary these categories are, look at the list of fruits that I enlarged. These include only fruits sold in U.S. supermarkets. Even in the United States, Safeway and Walmart do not define nature. But if there are no natural categories or descriptors, how can people judge wine? We can see the answer at the California State Fair Commercial Wine Competition. California's wine industry is huge, so this competition is a big deal. This chart will show how 4 judges rated 50 wines blindly without seeing labels. As you can see, they judge wines almost randomly. All 4 judges did agree that these 2 wines were unacceptable, and they tended to agree more on the worst ones than on the others. Yet 7 of the wines received both the highest and the lowest ratings simultaneously. All in all, above the bottom of this chart, the ratings look quite random. Again, this is the California State Fair Commercial Wine Competition. The judges there were some of the most experienced enologists in the United States, yet apparently they don't judge wines any differently than you or I. They like what they're used to, like newborns who learn to like anise in the womb. And they give a thumbs up or thumbs down to slight variations according to their biases. They're more knowledgeable than we are, so they're used to different wines than we and have developed different biases, but the mechanism of their aesthetic judgment is the same. There are no universal categories of flavor because there is no universal structure to the set of chemicals that we smell and taste. But there is a universal structure to the light that we see and to the pressure waves that we hear. This allows us to describe sights and sounds more objectively. The same structure exists in both light and pressure. It's a form of symmetry, but not the kind of symmetry you would normally think of. It's not repeating a pattern across space. It's repeating a pattern in different sizes, repeating a pattern across scales. To see an example, let's start with a line like this. Imagine it's a shoot growing up out of the ground. The shoot sends up 2 smaller shoots at the end, and those do too. And so on, again and again and again and again and again. Eventually, this forms a tree. A structure that repeats at different scales like this is called a fractal. A great many natural objects have a fractal structure, including real trees and bushes and our entire nervous system, cauliflower and all. So does the Canadian Shield. Small amounts of water flow downhill, form channels, and accumulate in puddles. Larger amounts of water flow downhill, form creeks, and accumulate in ponds. Even larger amounts of water flow downhill, form rivers, and accumulate in lakes. This mechanism happens at every scale and has made most of the Canadian Shield impassable except by canoe. These satellite photos show the result. They show the same parts of the Canadian Shield, but one of them is magnified 100 times more than the other. The black blotches are water, the grays are rock and forest. There's no way to tell which is the close-up. Fractal structures form a statistical regularity, a feature of nature that does not always appear, but appears more commonly than chance would allow. Since the brain evolved in a world filled with this statistical regularity, fractal structures, the brain evolved to respond to it efficiently. That's why the golden rectangle is easy on the eye. Every rectangle here has the same proportion, no matter what its size. But the fractal structure of the golden rectangle is so regular that we adapt to it almost immediately and find it dull. That's why Mondrian varied his rectangles to make their fractal elements imperfect, to make repetition, but with a lot of variation. Fractals also form the structure of the pressure waves that we hear as speech and music. Imagine a string strung tautly between two poles, with 3 balls on the string. If you swing the string up and down, the balls can move like this. Or they can move like this. Or like this. In fact, the balls will move all 3 ways simultaneously. Their movement will be fractal. The more balls we put on the string, the more ways they'll bounce up and down. Now imagine the string at a molecular level, a guitar string perhaps. At a molecular level, the string is formed by the equivalent of an infinite number of infinitesimal balls. This means that if you pluck the string, it will move up and down as a whole, in halves, in thirds, in quarters, in fifths, in sixths, in sevenths, in eighths, and so on indefinitely. Like this. This is how strings vibrate and string-like objects. Piano strings, vocal cords, the vocal apparatus of birds. Many surfaces vibrate similarly across their length and width, like cricket's wings or a drum. No real object vibrates so perfectly as this. The drawing illustrates a theoretical ideal, but most objects that convey information to the ears approximate it to varying degrees. These movements look like waves, and we call them waves. This particular set of waves is called an harmonic series, and each individual wave is called an harmonic. The first harmonic, the second harmonic, and so on. The relative proportions of the harmonics in this series determine the timbre we hear. The overall length determines the pitch we hear. Each wave is identical except for its size, so the structure is fractal. If you ever took a course in music theory, you learned about these harmonics, although you may have used the terms fundamental frequency, overtones, and partials. You probably were taught that the fundamental frequency determines the pitch that we hear. I don't want to disillusion you, but this isn't true. To hear a pitch, the brain does not need to hear the first harmonic at all. On a portable radio, the first harmonic is often too low to be reproduced. Even the first two harmonics may be too low. Yet we clearly hear the pitch of the bass notes of a piano or organ over a radio. That's because we don't hear individual harmonics, we hear the fractal pattern of harmonics. We hear pitch not from any single harmonic, but from the fractal pattern as a whole. All of our perceptions work this way. We sense an incomplete pattern, and the brain fills in holes. That's why you can recognize Adolf Hitler in this photograph, although only half of him is visible. Let's look at the information the brain uses for this. We'll look at sounds first, then we'll see how it also applies to sights. To see how we can hear harmonics that are not present, let's play with an electronic wave generator. Each of these sliders controls a single harmonic. H1 is the first harmonic, H2 the second, and so forth. Each harmonic can be set to any strength between 0 and 1. Here I've set the first harmonic to full power and left off the others. Let's switch on an oscilloscope and see what this looks like. Notice that the full length of the first harmonic exactly fills the width of the oscilloscope. Here I added the next 10 harmonics according to their theoretically perfect proportions. This wave looks very different from the first harmonic alone, but the full length of the wave still exactly fills the width of the oscilloscope, so we hear it as the same pitch. The different shape we hear as a different timbre, but the pitch stays the same. The same holds if I remove the first harmonic. This changes the shape of the wave, and hence the timbre we hear, but the full length of the wave still exactly fits the width of the oscilloscope, so the pitch we hear is still the same. Here I removed the second harmonic as well. Again, the shape has changed, but not the overall length of the wave. So again we hear a different timbre, but the same pitch. And now I removed the third harmonic too. Once again the wave's length is the same, and so is the pitch we hear. This shows the fractal structure of a wave to be more than the sum of its parts. It's an entity of its own, an entity that the brain has evolved to process so efficiently that it can fill in missing parts. In music, not only are pitches induced by fractal patterns, pitches also combine across time in fractal ways. The elements of rhythm and melody are fractal. The notation here makes this obvious. And composers often duplicate melodies at different speeds, sometimes in different parts, played simultaneously. Since all music is a set of fractals, different musical styles can be categorized by their characteristic fractal structures. Indeed, when you recognize a style, your brain is recognizing its characteristic fractal structure. Fractals are a statistical regularity of the physical world that brains have evolved to respond to sensibly. But even more fundamental is this particular fractal, the pattern of waves from a vibrating string. To understand this, let's first imagine that you want to describe a motion that never stops and never changes. You might come up with what the Greeks did, regular circular motion like this. That movement was continuous and uniform, or would have been with a better animation. But modeling motion that way ignores time. Time flows forward, so this motion needs to flow forward in time. We need to transform circular motion so that we can see it moving forward. This is how. These waves are called sine waves, after the Latin word for the folds of a toga. A sine wave represents regular circular motion through time. A taller sine wave denotes a larger circle. A faster sine wave denotes a faster motion through time. But a sine wave is just an elaborated circle, so the shape of every sine wave is the same. This shows how sine waves propagate in 2 dimensions. A loudspeaker is generating a single frequency. The dots are molecules of air. But of course, in the real world, these waves would propagate in 3 dimensions, as from the center of a sphere. Something like this. That last slide showed how energy passes through matter, how all forms of energy pass through matter. 200 years ago, a French mathematician named Fourier showed that the transfer of heat can be described by a combination of sine waves like these. Since the transfer of heat can be described that way, so can the transfer of any other form of energy, including pressure waves and light waves. This is a physical structure of the universe, so the brain has evolved to deal with it. To a large extent, the brain functions as a Fourier analyzer. When we hear a difference between a banjo and a flute, the brain is reacting to different combinations of sine waves. The brain analyzes pressure waves so efficiently that we actually hear most of their information before they've had a chance to finish a cycle, while they're wavelets rather than proper waves. The initial wavelets are what the brain uses to define most sounds. To the brain, wavelets distinguish a cot from a dot from a tot. Light also travels as sine waves, only not waves of molecules, waves of photons. Since everything we see is a reflection of light, everything we see is a combination of sine waves, just as everything we hear is. Light waves travel faster, but there's no fundamental difference between them. Fundamentally, the only difference is how we sense them. Waves of air pressure reach the eardrum from a single direction, but waves of light enter the eye from every direction. This means that just as any sound can be described by a combination of sine waves, so can anything we see. The only difference is that describing the waves we see requires describing the waves using an additional dimension. This is difficult to wrap your head around, but it's sort of like saying that you can paint any scene using a set of paintbrushes differing in size. Here's an example. Here are perceptual equivalents of 8 harmonics forming a photograph. I began this talk by showing that the senses are neither separate nor distinct. Then I showed how we learn to enjoy our perceptions. And then I showed that harmonic frequencies and fractals structure the energy that we sense. Now let's leave the lab and look at these phenomena in the real world. Let's use this framework to compare some sights and sounds of the 18th century to their equivalent today. We will start by seeing how the everyday fractal structures of two eras differ. Then we'll see how those differences affect some of our preferences in ways that carry across all of our sensory systems to affect how we enjoy all of the arts. Imagine you're a musician in the 18th century. You're going to Dresden to play the Palace. Literally to play the Palace, not to play the Palace Theatre. As you walk in, you see this nice piece of modern architecture, the Palace Church, which is now the city's cathedral. It has lots of repetition and lots of variation. Some of this repetition is across scales, as you can see here with these ranks of sculptures and balustrades. I don't know if they're different sizes in fact, but they look different from the street. And of course, each sculpture is unique. Internal elements also echo one another in different sizes, like these arch-shaped cornices. In contrast to the Cathedral of Dresden, here we have the Cathedral of Modernity. It also repeats elements, but it shows little variation. And here's an aesthetic descendant of the Bauhaus, the Juilliard School in New York. Again, the fractal structure of this is obvious, but the variation is not. This and similar buildings is where most musicians today learn to play 18th century music. Here's the inside of the Palace Church. Its decoration is simpler than the outsides. It's moving toward the 18th century's avant-garde. Again, repetition and variation as an assortment of scales. Stunningly elaborate decoration, with lots of elements that are similar but different across a range of sizes. We always hear that the classical aesthetic was simple and elegant, but simple meant something different then. This is an example of what simple meant then. This illustrates the ideal of simplicity in a book on interior decoration published in 1812, when simplicity was mainstream rather than avant-garde. Quote, "The nature of every piece of furniture is its function, the practicality for its use. What remains for art? To refine the forms dictated by convenience, to combine them with the simplest contours, and to carry out these essentials without ever disguising its character." Walking around this chair, you would see a lot of repetition and variation, with some similarity across styles as well, like this. This is the sort of space an 18th century musician might perform in. Notice the interior design has repeated spaces of different size at different scales with lots of decoration. Here is the concert hall at Juilliard. Unending repetition, little variation, no decoration. At an 18th century concert, you might see clothing like this. For women, the common pattern is two sides in the center, intricately decorated. Perhaps decorated like this. The structure's fractal repetition is obvious, and so is its variation. In contrast, this is the most elegant dress I could find on Christian Dior's website. You might call it Bauhaus fashion. The modern dress does have a fractal structure. It repeats triangles at a few scales and by inversion, but the difference in complexity is obvious. In the 18th century, every formal performance of anything musical included at least one minuet. A minuet was a stately dance for a ballroom full of aristocrats in fancy dress. It formed a moving structure of people within the room, a regular structure that evolved in time with both similarities and differences of dress and of gesture, all at different scales, a fractal evolving in time. The steps were tricky to execute. When I play this film clip, you'll see that the men are often on their toes, and you'll see a lot of graceful and subtle bends of the knee and turns of the leg. Because it's difficult to execute, it is a slow dance. It is played slowly in units of 6, and within each unit of 6 you can hear a lot of variation. This is a good demonstration, although if it had been a real ball with an orchestra that size, there would have been 5 to 10 times as many dancers. In contrast, here is a modern performance of the same piece by a Toronto group specializing in early music. Minuets are usually played like this nowadays. Nobody could dance a minuet at this speed. Note that the gently variegated units of 6 have been replaced by mechanically repetitive units of 3. I chose dance music as my illustration because nearly all of Western music used to be dances. Of course, much of it was sung, but even the songs could usually be danced. Musicians would naturally make sure of this because they were primarily dance musicians. If they played something other than a dance, it would have been a gig they were doing on the side. And there was reason for this. Reason coming from the cauliflower, from the sensory mixing inside the brain. I mentioned earlier in this talk that hearing and moving are intertwined, and so are sight and touch. Remember this bizarre finding. In this experiment, the man in red feels both of his hands being stroked. In fact, hearing and movement and sight and touch intermingle with social perceptions too. If we hear and move together with a bunch of other people, and if we see them moving at the same time, then we feel ourselves attached to them more than to other people. That's why armies drill recruits. Generals don't expect soldiers to charge a machine gun in strict formation. They drill recruits because marching in formation forms the soldiers into a cohesive social unit. a unit that works together well and in which each soldier feels responsible for the others. The same holds with dancing. That's what got people dancing and kept them dancing. By dancing the minuet together, aristocrats fitted themselves together as the ruling class. Peasants learned to cooperate by dancing a raucous Ländler. Priests bound themselves together by processing together in church. Before people could sit in front of a screen, they amused themselves by reading, or they made their own entertainment. They learned dances and they danced. From millennia before Mozart through the Second World War, everybody danced. This ended in the 1950s with television. To see how important dancing used to be, let's look at this video clip from the UK. In 1929, this was the equivalent of a major feature on TV news. It's from a newsreel, a precursor of TV news that you would have seen in any movie theater before the feature.
Well, Molly, shall we dance this new dance?
What, the new 6/8?
Yeah.
I'd love to. Now, girls, I'm going to explain the steps to you. They're very simple. Now, the first movement is a walk and an open chaise. So you count half a bar to each walk. Now, will you watch me? Walk, 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 slide, close, forward. Walk, 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 slide, close, and forward. Now, the next
So there you have it, an overview of aesthetics based on science. We can boil it down to three main points. First is that the cauliflower handles all sensory signals similarly and often mixes them up. Average experiences form our basic preferences, and depending upon our biases, slight deviations bump these into beauty, ugliness, fear, or comedy. The physical world is largely fractal in structure, so the cauliflower evolved to process fractal structures efficiently. This makes variations from average more noticeable. Since all of this is based on experience, you might conclude that everything about aesthetic perceptions is learned. You might conclude that aesthetics is the triumph of nurture over nature. But this is the distinction without a difference. Nature and nurture are two sides of one coin. They can't be divorced. Learning is done by a physical substance, by tissues of the brain. The brain can learn because its tissues are malleable, and that malleability is physiological, a product of nature. That malleability also has some natural limits. For example, yellows look brighter than blues. To everybody, everywhere. This is built into physiological machinery. No amount of experience can make them equal. And physiological machinery defines these universal colors. If you give people color chips and ask them to sort like with like, you end up with these 6 piles. This happens everywhere, even in cultures that don't have any words for colors beyond dark and light. The transitions vary. What one person calls blue, another may call green. and those transitions will vary with experience, but these 6 colors are built into the visual system. They are the primary colors we perceive. However, there are very few specific physiological primitives like those. Virtually all specific aesthetic preferences are learned. They begin with something familiar, like this scene. I'm sure you've seen scenes like it in the movies. You've never seen this particular one, but you've seen a lot that resemble it. It looks perfectly pleasant. It's not a picture you look at for long, but neither is it something you shut your eyes to. But let's see what happens if we change it just a little. These changes carry the picture into a different realm. Optically, this picture is not very different from the other, but the small change makes a significant difference to how you perceive it. How you react to the change will depend upon biases that you have developed. Those biases will push you toward finding it beautiful or ugly or funny. That is the basic story. To learn more about this, I'm afraid that I don't know any place to send you except to our book. However, you will find a lot of information there. Its concepts can be hard to wrap your head around sometimes, but we wrote it for general readers as well as scholars. You'll find the table of contents and 2 sample chapters on this website. I'm very pleased that you took the time to listen to this talk. I do hope you found it interesting.